Fundamentally, there's a lot at stake because we're trying to answer something really big. How did the universe begin? Did time begin with the Big Bang? And after the universe began, it then went through a really rapid period of expansion called inflation. That's one possibility. Another possibility is the universe didn't begin with the Big Bang, but rather has gone through a cycle of collapse and then re-expansion. That second model is called the ekpyrotic universe. Those are two very different theories of how the universe began, two very different theories of the universe's origin. And what we're going after is to try to distinguish between those two theories. And what's exciting about doing an experiment like this, we're going to do a measurement. We will ideally show that one of these theories is wrong. If the inflationary model is correct, then it predicts it should produce gravitational waves. That'd be a great triumph for the inflationary theory. And more importantly, would mean we'd have to abandon any alternative theory that doesn't predict gravitational waves.
I see the Simons Observatory as the ultimate time machine, being able to look back to when not only light predated light, but gravity, and when the universe itself, when gravity potentially was still in a quantum state, when all the matter and energy in the universe were in this ultra-compactified configuration, or not. And if we do see that, how exciting would that be? But even if we don't see that, what does it tell us about these other laws? We'll be able to either detect quantum gravitational waves from the Big Bang's inflationary epoch, which would be incredible, an incredible feat, or we could potentially have better understanding that perhaps the universe didn't originate in an inflationary expansion, but was actually, there was a universe before ours. And just as we want to know our universe's origin story, now there'd be an answer to that question of what happened before our universe.
So for the last 50 years, the prevalent idea has been to assume that the universe began with a bang. There was nothing and then something. If you begin with that idea, though, you immediately run into trouble. This sudden beginning, due to the effects of quantum physics, produces a universe in which the distribution of matter and energy is extremely non-uniform. It's actually not what we see. We observe a universe which, on the large, is extremely uniform and which seems to be flat. The question is, why? Well, if you assume the universe began with a bang, the only way that has been proposed to explain how it would be smooth and flat is this idea of inflation. It turns out that if you begin to expand the universe at this accelerating rate, quantum physics takes over and totally distorts what happens next. Instead of producing everywhere a universe that looks like us, it actually produces a patchy universe with an infinite number of patches which have different properties, and this is what's called the multiverse. This multiverse idea kills all the advantages of the theory, because instead of explaining why the universe is as the way it is, it actually produces an infinitude of possibilities. Suppose the bang were instead a bounce. Suppose space and time existed before this bang. And instead of the universe springing from nothing, there was actually a long, slow period of gradual contraction. Slow enough for the universe to interact with itself, smooth out the distribution of matter and radiation, bounce, and then produce an expanding universe like with the properties we observe today.
With astronomy, we have to wait for these things to come to us. I have to use what comes to me. It's like being on the ocean and getting driftwood and trying to learn about where was this forest, where this piece of wood came from, an ultimate message in a bottle. And with this telescope, we look back in time, not only to when there was light, but to when there was gravity and when the universe existed. So the time that gravity existed predates the time that the CMB was formed. So we can actually look back farther in time and in space using waves of gravity. So if these waves of gravity are seen, it would be the earliest possible way to look back into time. Along the way, we're going to find out so much else about the universe in addition to this. Gravitational lensing, gravitational waves, the presence of dark energy, dark matter, neutrinos, particles, fields, energy. So all of this is guaranteed to be accomplished by the Simons Observatory.
In many ways, the Simons Observatory collaboration is a community of dreamers. We're dreaming of making some advance that will give us a deeper insight into physics. And it's that common dream that drives us to the mountaintops. It's like building a cathedral. There's lots of pieces, and we're all building our own piece, and you don't want the cathedral to collapse. We're pretty close to converging on a detailed concept of what this observatory will look like. How will we build the telescopes? What instruments will we build? And how will the pieces all come together?
I'm always surprised when we finish an array because they are beautiful, and then you put it in, and then you're into the actual telescope, and then you're actually getting data from it, and the data are incredibly sensitive, and usually I've lost sight of how amazing and good the device actually is because of being constantly worried about the small things about it.
Often in scientific experiments, people, whether they're scientists or the general public, think it's really important that you detect something and are disappointed when you don't detect something. But it's important to realize that not detecting something can often be very informative, maybe even more informative than detecting something. And this would be an example like that. So not detecting these gravitational waves, or not detecting the B modes, which are the imprint of those cosmic gravitational waves, would be telling us that the beginning of the universe isn't what we thought it was, a bang. In fact, it didn't have to be a beginning at all, but there was this bounce instead.
The question of whether the pursuit of arcane knowledge is valuable is one I think about all the time, and I usually come back to thinking that it's similar to art. We're not robots and automatons, and you need to find and experience beauty, and you need to find beauty in thinking and in your mind and your understanding of the universe.
It's true that in this world there are many more practical problems to be solved, issues about helping humanity to live life better, improving the climate. All those questions have to be pursued as well. But spending a small amount of effort trying to also satisfy our curiosity, I think just makes life more meaningful for humanity on this planet.
We may not know if inflation took place because inflation might not have taken place. Or maybe it did and it was so feeble and so weak, and we can't understand why something so feeble and so weak could make such a munificent, beautiful universe. But I think it's kind of a wonderful position to be in, that either alternative is kind of mind-bending in its own way. It's not for me to say which is more mind-bending. It's privileged to be able to, shed light onto either of these two just fundamental possibilities. And I think that's the most exciting, mesmerizing question of all, that which of these two will be right, not which do I prefer.